Assalamualaikum warahmatullahi wabarakatuh. My name is NURUL SHAFIQA binti Muhammad RIZAL. My metric number is SX23030EMMHS01. Today, I want to explain some example on application of copper-aluminium or bronze in engineering. Copper-aluminium are used in electrical connectors such as bus bars and wiring due to their high electrical conductivity and corrosion resistance. Okay, next, marine equipment. Copper-aluminium are employed in marine environment for fitting, propeller and shipbuilding component due to their resistance to seawater corrosion. And lastly, automotive part. CU alloy used in automotive application for parts requiring a combination of strength, lightweight and corrosion resistant, such as radiator tube.
Type of alloy: copper aluminium, percentage copper. Alloy: copper at 2% aluminium. Transformation during solidification. The copper 2% aluminium alloy starts as a liquid at high temperature. As it cools and reaches the liquidous line, a primary alpha FCC copper rich phase begins to solidify. Solidification continues and more alpha phase forms until the eutectic temperature at 548 degrees Celsius is reached. At the eutectic temperature, the remaining liquid transforms into eutectic mixture of alpha and beta phase. Microstructure sketch: a primary alpha phase grains, a small amount of eutectic mixture alpha plus beta in the grain boundary. A cooling curve: initial drop as the liquid cools. A plateau at the liquidous temperature where the primary alpha begin to form. Another plateau at the eutectic temperature 548 degrees Celsius where the remaining liquid transforms into eutectic mixture alpha plus beta. Composition and phase at 500 degrees Celsius. At 500 degrees Celsius, the alloy consists mostly of alpha phase and beta phase. Using the lever rule of the phase diagram, the amount of each phase can be estimated.
Second, hypoeutectic alloy. For 10% copper, transformation during the solidification is liquid begins to solidify into primary alpha phase. When the temperature reaches 548 degrees, remaining liquid transform into alpha and beta phase. Microstructure of this hypoeutectic alloy is primary alpha phase surrounded by eutectic mixture of alpha and beta. The cooling curve initially drop, plateau at the liquidous line, another plateau at the 548 degree. Composition and phase at 500 degree is mostly alpha phase with some beta phase. On the next slide, I already prepared the sketch on the cooling curve, also the phase diagram and the microstructure on each phase of the phase diagram.
Hello everyone, my name is Siti AISHAH binti MOHAMED. Today I will talk about eutectic and hypereutectic alloy. For copper and aluminium, eutectic steel has a composition of 33% of copper atom and temperature at 548 degrees Celsius. Upon cooling, austenite will transform into pearlite, ferrite, cementite in laminar microstructure. The eutectic microstructure discussed above are example of regular or normal eutectic where the goal of the two solid phase is coupled. The resulting cooling curve show the two stages of solidification with a section of reduced gradient where a single phase is solidifying and a plateau where eutectic is solidifying. For the composition and phase at 500 degrees Celsius, we show the compass of alpha and beta phase in a lamellar structure. When the composition of an alloy placed to the right of the eutectic point, it is called hyper-eutectic. The liquid begins to solidify into primary beta phase. At 548 degrees Celsius, remaining liquid transforms into a alpha and beta phase. Consider mixture of alpha and beta so that the overall composition at the alloy place it to the right of the eutectic point. Initially, the alloy is a high enough temperature to ensure that the mixture is fully liquid. For the hyper-eutectic alloy, a couple-rich primary phase in the hyper-eutectic alloy practically eliminates the initial eutectic undercooling observed in hypoeutectic and eutectic. The composition and phase at 500 degrees Celsius will show the mostly beta phase with some alpha phase.
Assalamualaikum, my name is NURHAZIQA binti SARBANI. I will explain about copper and aluminium. For copper, which is a copper of 48%, and phase is a paritetic alloy, which is a paritetic alloy. What happened is a transformation during solidification, which is liquid plus beta transform into gamma phase and liquid at paritetic temperature. For microstructure, primary gamma phases surrounded by transform beta phases. For the cooling curve will drop to paritetic transformation temperature, then further drop. For the composition and phases at 500 degrees Celsius, mostly gamma phase with minor B phase. For the cooling curve microstructure, will be shown at the report. Okay, next is a method of improving material properties, which has 5 methods. First is alloying, adjusting the composition of the alloy by adding other elements and can enhance properties like strength, corrosion, resistance, and conductivity. For copper-aluminium alloy, adding small amount of element like iron, magnesium, or silicon can modify its mechanical and chemical properties. Second, method is heat treatment, which is involve heating and cooling the alloy in a controlled manner to alter its microstructure, thereby influencing properties such as hardness, toughness, and ductility. For copper-aluminium alloy, heat treatment can refine grain structure and improve mechanical strength. Third method is cooling working. Also known as cool deformation or cold fogging. This process involves plastic deformation at temperature below the realization point. It increases hardness and strength while reducing ductility. Fourth method is a surface treatment. This surface treatment is a technique like painting, coating, or surface modification can enhance properties such as wear resistant, corrosion resistant, or aesthetic. Five method is a control cooling. By controlling the rate of the cooling during solidification or after heat treatment. The microstructure of the alloy can be tailored to achieve desired properties. So the 5 methods that can improve material properties. That's all for me. Thank you. Last but not least, conclusion on copper-aluminium alloy. We can conclude that the copper-aluminium alloy system exhibits distinct solidification behavior across authentic, hypoauthentic, and hypereutectic composition. Each composition influences the microstructure formation, cooling characteristic, and phase composition, making a copper-aluminium alloy versatile for various industrial applications. Understanding these properties is crucial for optimizing alloy performance and tailoring them to specific engineering requirement. This reference we got from ASM International, ASM Handbook Volume 3, Alloy Phase Diagram. This handbook provides comprehensive phase diagram and explanation. And we got from Masauki TB, Binary Alloy Phase Diagram. Reference contain detailed information on binary phase diagram, including aluminum cuprum. And we got this also from Callister WD 2007, which is a material science and engineering and introduction. This textbook covers phase diagram and transformation in detail. So that's it. Thank you.